Hello, welcome to the Day 6 notes on polynomial functions, section 6.3. Today what we're going to be doing is stating the degree and leading coefficient of a polynomial, evaluate polynomial functions, and describe the end behavior of a graph of a polynomial function. So here's the technical definition of what a polynomial in one variable is. So basically what I want you to notice from here, because you don't have to memorize this or anything, but the powers of n, notice, are going down. And then finally, this dot, dot, dot means there's other things in this spot there. And then it's 2 power of 1, and then there's no x there, which means it's x to the 0. Also, I do want you to notice that the only variable here, because a is not equal to 0, and all these coefficients are real numbers. And n is a non-negative integer. So basically, a polynomial in one variable, all we have is the same variable appearing, but it will be raised to different powers. Okay, so a polynomial is written in standard form, it's called. When the values of the exponents are in descending order. So you're going to take the terms and write them so that the value of the exponents is going down. The degree of a polynomial is the value of the greatest exponent, so whatever the largest value is, that's the degree of the entire polynomial in one variable. And the coefficient of the first term of a polynomial in standard form is called the leading coefficient. Oops. Okay, so that's going to take us to the first part, the first type of example. It's going to say state the degree of and leading coefficient of each polynomial in one variable. If it's not a polynomial in one variable, explain why. If it is, write it in standard form. So the first thing you want to look through is there only one variable? Because if there is only one variable, then it is a polynomial in one variable. I just said one variable like 5 times, maybe 6. So looking at the first one, we have negative 4x squared plus x to the third plus 3. I only see x's, so it is a polynomial in one variable. So I'm going to write in standard form. Again, standard form, I have to write the terms. So this one has 3 terms, meaning, you know, what's separated by addition or subtraction as a 4x squared, x to the third, and a 3. I have to write it so the powers are going down. So I'm going to start with x to the third, and then minus 4x squared, and then plus 3. So let's talk about the degree. The degree is the value of the greatest variable or exponent, so it's 3, and then the leading coefficient is the coefficient, remember up here, of the first term when it is in standard form. So our first term here is x to the third. That coefficient would be 1. Okay, looking at part B here, first you still just want to look through, make sure it's all one variable. I have 5x squared minus 2xy. Well, there we have it. We have 2 variables. Because of the x and a y, it's not a polynomial in one variable, so that's our reason. Not a polynomial in one variable because there are 2 variables. Okay, I would like you to attempt to see on your own. Again, decide whether or not it's a polynomial in one variable. If it is, write in standard form and then state the degree and leading coefficient. So please pause the video and then compare your answer to mine. Okay, here's the answer. If you didn't get that, please make sure to ask in class tomorrow and find out why you got it wrong. The second part of today's lesson is to evaluate polynomial functions. So we're going to find r of negative 2 and r of 3 for each of these functions. So they gave us r of x is it's negative x squared plus 2x minus 5. Now for a problem like this, I do think it helps to, instead of thinking of it as negative x squared, to think of it as a negative 1 in front of that x squared. Actually put that coefficient in there. So all we're going to do is we're going to find what r of negative 2 is. So wherever there was an x, we're going to replace it, but everything else is going to stay the same. So I'm going to switch colors here and just replace x with negative 2, wherever I left a little space there. Okay, so going along, we're going to have negative 1. Now if I square negative 2, squaring anything, positive or negative, is going to give you a positive answer. So it's 4. Then we have minus 4 minus 5. So this will equal negative 4 minus 5, which is a grand total of negative 13. To find r of 3, we're going to do the same thing. We're going to plug in 3 wherever there was an x. So we will get negative 1. I'm going to do the parentheses with a different color again. And put a 3 in there for the x. Oops, I forgot that squared. Alright, so we get negative 1 times 9 plus 6 minus 5, which is negative 9, plus 6 minus 5 gives me a grand total of negative 8, because negative 9 plus 6 is negative 3, and then minus 5 gives me negative 8. Okay, I would like you to try B on your own. You have a new r of x. It's 4x to the third minus 8x. I would like you to find r of negative 2 and r of 3 for each, or for that function. Okay, there are the answers to part B. So if you did not get those, please make sure to ask in class tomorrow. Okay, now looking at example 3 and 4, they become a little bit more complicated because we're not just replacing the x with a number, we're replacing it with, in this case, a monomial, sometimes, so one term. Sometimes it's going to be a binomial. So here we have a variable still that we're replacing with, but we're still going to do the same exact thing we did before. So we're going to write p of 3a equals 2 times, I'm going to leave the parentheses there, something new being squared plus 1, and that something new is this 3a. Okay, so going and evaluating this, we're going to get 2 times 3a to the second power. This is from the first section of the chapter. You have to square the 3, giving you a 9, and then you have to square the a, so you get a squared plus 1, and you get 18a squared plus 1. So remember, order of operations is important. The whole please excuse my dear Aunt Sally. Notice that I evaluated exponents first. I did the 3a to the second power first before I multiplied the 2 and the 3a. And so that's going to be important. You have to follow the order of operations. This is my final answer. These are not like terms, so I can't do anything else with it. Remember, you can multiply whatever you want. A squared times a to the third, you get an answer. It's a to the fifth. A squared plus a to the third, you would have to leave that because they're not like terms, meaning same variable to the same power. Okay, let's take a look at example 4, our last example of this type. We're finding t of a squared for t of x equals negative x squared plus 7x minus 1. Again, with that negative in front, think of that as a coefficient. Think of it as a whole separate entity from the x squared. There's a negative 1 times an x squared. So when I plug in, it's going to be t of a squared equals, I'm going to write that negative 1, and I strongly suggest you do so you don't make a mistake there. And now where the parentheses are, I'm replacing it with a squared. Alright, evaluating order of operations, I'm not going to multiply negative 1 times a squared. That's not what I'm going to do first. I leave the negative 1 alone. I square a to the second, and that gives me a to the fourth. Plus, I can multiply these, it's 7a squared minus 1. I'm just going to clean this answer up a little bit and write it as negative a to the fourth, or negative 1 times a to the fourth, plus 7a squared minus 1. And that is my final answer. There are no like terms, and it's a polynomial in standard form because my powers of the exponents are going down. So just a quick recap, if I was to ask you for the degree of this, hopefully you would tell me it's 4, and if I asked you for the leading coefficient, hopefully you would tell me that that is negative 1. Alright, so the final part of today's lesson is the end behavior of polynomial functions, and to do this we have to look at the graph and see what's happening basically when we're looking as it moves away from the origin, as we're no longer seeing what the graph is doing. So I'm going to go ahead and pause it and write the definition, the technical definition of end behavior, because I think it's going to be a lot faster for you to copy it down rather than wait for me to write it with you at the same time. Okay, so here you have the definition. The end behavior is the behavior of the graph of f of x as x approaches positive infinity, and the way we abbreviate that is x and then an arrow positive infinity, and what this means is x is moving to the right and negative infinity, and again we would write x and then an arrow negative infinity, and this is as you look to the left, as x moves to the left. So you may want to pause at this point and write that down because that is important. Okay, there are two things we use to determine the end behavior, and the first one is the degree of the function. And we look to see if it's even or odd. And then we look at the leading coefficient. And for that, we look to see if it's positive or negative. Okay, degree, even or odd, leading coefficient, positive or negative. So there are 4 cases that can happen. So the first ones that we're going to talk about is if the degree is odd. Okay, for both of these. Now the first one, let's do a leading coefficient that is positive. The best way to remember this is think of, I'm just going to draw a coordinate plane here, the smallest odd degree function. Odd meaning 1, 3, 5, 7, right? The smallest odd degree is 1. A function with a degree of 1 would be a line. And if the leading coefficient's positive, that line is going to be, the slope is going to be positive. So basically what I drew here is f of x equals x. Okay, that's the smallest odd degree positive leading coefficient function. So end behavior is what is the graph doing? So the black line, what is it doing as x approaches positive infinity and as x approaches negative infinity? So x approaching positive infinity, this is, you're looking as you go to the right, what is the graph doing? Well, it's going up, so f of x, that's the graph, is also going to positive, it's approaching positive infinity. Now as x approaches negative infinity, you're looking to the left. So you're moving to the left, you're looking, what is the graph doing? It's going down, so this answer would be f of x approaches negative infinity. Now the graphs that we're talking about are going to be higher degree, so instead of being a line, and you don't have to draw this, but it's going to be something like this. Okay, there's going to be bumps and hills and valleys and different things are going to be happening, but notice that the end behavior, what's happening at the ends, is identical to a line because we're used to how a line looks. Now the domain of this, it's what values of x would it be? It goes left and right forever, so it's all reals. And then the range, it's going to be going up and down forever. Nothing's preventing it. It's not starting at a certain point. It goes up and down forever. That's also all reals. Okay. Back to the next example, we have an odd, but if the leading coefficient is negative. So again, the most simplistic example of this would be a line, because that's an odd degree. And now if the leading coefficient is negative, that line would have a slope that's negative, so it would be going down. Okay, so end behavior. As x approaches positive infinity, so you're looking to the right. As you're going to the right, where's the graph going? What is it approaching? It's approaching negative infinity. And as x approaches negative infinity, so as you're going to the left, what is the graph doing? It's going up. So f of x approaches positive infinity. Again, for this, the domain, what x values can it have? It can have all reals. There's nothing that's stopping it. There's no walls. And then the range is also all reals because the range you're looking up and down. There's no ceiling or floor. I think that's how we described it in previous chapters. Now again, the functions we're going to be looking at aren't going to be lines. They're going to be things to the 7th power, to the 9th power, but their end behavior is going to be identical if it's an odd degree function with a negative leading coefficient. So it could look something like that, but notice that the end behavior, what it's doing on both ends, is the same. Okay, let's talk about the last 2 cases, and they're going to be if it's an even degree polynomial. So hopefully you're all thinking about the smallest even degree polynomials that we've already done. And what would those be? You guessed it, quadratics, parabolas. So let's do first a even degree polynomial with a positive leading coefficient. So I'm going to draw the most simplistic, and again, even the smallest even degree that we've ever talked about is a parabola, a quadratic. Now, hopefully you remember that if a parabola had a positive leading coefficient, if you remember that was the a value, it would open up Okay, so let's talk about the end behavior. What is this graph doing as x approaches positive and negative infinity? So positive infinity, you're looking to the right. What is the graph doing? It's going up. So this would be that f of x approaches positive infinity. And then when you're deciding as x approaches negative infinity, you're looking to the left. What is the graph doing? Notice that it's going up. So f of x also approaches positive infinity. So a lot of times you think about this as a field goal. When it's even, both arms would be up. Again, we're going to do higher degree things. There's going to be, w to the 8th or something like that. So it's going to look like this or whatever. But the end behavior is the same. On both ends it's going up. So f of x approaches positive infinity. Okay, domain and range. The x value, it continues left and right forever, this function. There are no walls, so it's all reals. And then the range is there a floor and ceiling? And here there is a floor because it starts right here and then it continues up. So it's going to be that the range is, the y value is greater than or equal to the min. Because there will be a min value just like with the parabola. Okay, now to the last case. If you have an even degree, but the leading coefficient is negative, hopefully you're picturing our most simplistic example, it would be a parabola that is opening down. Because if the leading coefficient is negative, that's like our a value being negative, so it would open down. So it's like a reverse field goal in football. Okay, as x approaches positive infinity, you're looking to the right. What is the graph doing? It's going down, so f of x approaches negative infinity. And as x approaches negative infinity, you're looking to the left. What is the graph doing? It is also approaching negative infinity because it is going down. Domain and range. X, there's no walls here. This thing continues left and right forever, so it's all reals. The range, it has, if you remember from, I believe, chapter 2 when we talked about it, it has a ceiling, and then everything is going to be below it, so it's going to be y is less than or equal to, and in this case it's not the min, it's the max, because that's the maximum value that x would be. And again, in between the polynomial functions we're going to be looking at, there's going to be other crazy things happening, but the end behavior is identical to this. Okay, so from here on out, we're just going to be doing examples. So here, for each graph, we're going to describe the end behavior. We're going to determine whether it represents an odd degree or even degree polynomial function, and we're going to state the number of real zeros. The number of real zeros is the number of times, if you recall from previous chapters, zeros are where the graph crosses the x-axis, so that's the number of times it crosses the x-axis. Okay, so first thing, let's do end behavior. So we actually have one of the examples I gave in the first one. It's a line. So as x approaches positive infinity, as you look to the right, what is the graph doing? It's approaching positive infinity. And as x approaches negative infinity, you're going to the left. What is the graph doing? It's going down. So that's negative infinity. Now, is this an even or odd degree function? It's a line, so we could see that it's an odd function. An even degree function is always going to be the same. F of x is either going to be going up both times or it's going to be going down both times. An odd degree function is one's up, one's down. So it's kind of acting strange, like why aren't you together or something. Okay, number of zeros. How many times does this thing cross the x-axis? I'm looking right here. I see 1. So there's one real zero. Next one. As x approaches positive infinity, you're looking to the right. What is the graph doing? It's going down, so that would be negative infinity. And then as x approaches negative infinity, as you look to the left, what is the graph doing? It's going down. That's also negative infinity. So like I said, the oddballs are the one where it's like one is up, one is down. The ones that are even do the same thing. They either both go up, both go down. So this is an even degree function. And then the number of zeros, we're going to count how many times this crosses the x-axis. I got 1, 2, 3, and 4. So there's 4 real zeros. Alright, I would like you to pause the video and actually try this last one on your own and then check your answer with mine. Okay, there are the answers. If you did not get those on your own, please make sure to ask your teachers tomorrow because I know this is new and it could be rather confusing. Okay, last few examples here. Instead of being given a graph, you're going to be given an equation, and you're still going to have to describe the end behavior of the function. So let's do the first one. G of x equals 2x to the fifth plus 6x to the fourth. It's very important that you have it in standard form, and then you want to write down the degree and the leading coefficient. Now, I'm not saying the actual values of those. Remember, the degree that we care about for these end behavior problems is we care, is it even or is it odd? So our degree here is 5. So 5 is an odd degree function. And then you care also about the leading coefficient, and you don't care if that's even or odd. You care if it's positive or negative, and in our case, it's positive. So what I would do is sketch yourself a little graph. What is the most simplistic odd degree function with a positive leading coefficient? Just to give yourself that visual so you could see or think, what does that look like? Hopefully you realize an odd is a line, and if the leading coefficient is positive, that would be a line that has a positive slope. So I think if you sketch that, that's going to help you describe the end behavior. So as x approaches positive infinity, as we're looking to the right, what is the graph doing? It's going up, so it approaches positive infinity. And as x approaches negative infinity, as you look to the left, the graph is going down, so it approaches negative infinity. And again, we decided that the degree is odd, so that means they're different. They're not the same, they're kind of oddballs. One goes up, one goes down. Okay, part 2, or example 2, we have h of x equals negative 8x to the 7th plus 2x to the 6th minus 4x. Again, our two important things are degree and leading coefficient. So let's go ahead and see what those are. This polynomial is in standard form because the powers of x go down, notice. So the degree is odd because it's 7. And then the leading coefficient is negative 8, so it's a negative number. So remember, degree, we want to see if it's odd or even. Leading coefficient, positive or negative. Let's sketch the little graph for ourselves. Hopefully you realize odd degree functions are the most simplistic, are lines. This would be a line that's going down with a negative slope. So as x approaches positive infinity here, as you look to the right, what is the graph doing? It's going down, so it approaches negative infinity. And as x approaches negative infinity, you're looking to the left, the graph is approaching positive infinity. Okay, please try example 3 on your own, so pause the video and then check your answer against mine. Okay, there's the answer, and as always, if you did not get that on your own and you're confused, please make sure to ask your teachers in class tomorrow. Thanks, have a good one.